to lecture 7. In this lecture, we will give a lower bound of any comparison sort. So the meaning of a lower bound here means for any comparison sort, we will show that it needs to take certain running time at the minimum. Such a lower bound applies to insertion sort, selection sort, bubble sort, heap sort, merge sort, and quicksort that we have studied. But it doesn't apply to counting sort, Radix sort, and bucket sort. The technique here will be based on something called the decision tree model. So let's start. First of all, a comparison of two items can tell which item is larger, but we will not know the values of the items. So it is like the items are all locked into boxes, and then we can at any time choose any two boxes to compare. But we don't have the values inside. A judge will tell us that which box contains the larger value. So this is a comparison, and comparison sorts will only use comparisons to deduce the relative order of items, so that we can then use this information to sort the items. Now, merge sort and heap sort are the fastest comparison sorts we have studied so far. The worst case running time is big O of n log n. And we may wonder, do we have comparison sorts that runs in little o of n log n time? And in this lecture, we will show that the answer is no. In particular, this is the main theorem that we are showing. We want to show any comparison sort uses at least, so this is omega n log n comparisons to sort n distinct items in the worst case. And the remaining of this lecture proves this theorem. Now, if it is true, because we know that each comparison will take at least constant amount of time, so because a comparison sort uses omega n log n comparisons, so it needs omega n log n time. So if it is true, if this theorem is true, then it means that any comparison sort runs in omega n log n time. Now, the reason why we choose to focus on comparisons is that if it is the case, then we may assume all the other operations, such as swapping or moving items around or calculations, will be for free. So they will not be counted because they are not comparisons. In that case, a comparison sort, we can switch a little bit of its order and we can build it to work like the following. So it will first make a series of comparisons between items, and then it may take unlimited number of free operations to find out the correct order of the items. And then running a comparison sort on different inputs, which means we have the different sorting order of the items given from the beginning, will then be captured by something that is like a tree. So we will show what the tree looks like, but then in general, the tree will have internal nodes, and then each internal node corresponds to a comparison, and the branch of the internal node corresponds to the result of the corresponding comparison. And finally, the leaf of the tree will represent a particular sorting order. And this tree that captures the running of a comparison sort on different inputs is called the decision tree of the algorithm. So let us see an example. So we have the following comparison sort, okay, for 3 items. And then we will see how its decision tree look like. So we consider this method. So we have 3 items A, B, C. So this method corresponds to always sorting 3 items only. So it has 3 steps. always, the first step will compare A and B, and then the second step will always compare A and C, and the third step will always compare B and C. Now, after we have made these three comparisons, then the algorithm can do some calculation, and then after that, deduce the order of A, B, C based on these results. So the corresponding decision tree looks like this. So at the root node, this is corresponding to the first comparison that we are making. We are always comparing A and B. Then depending on the output, so there are two possible results of comparing A and B. Either A is smaller than B or A is larger than B. So it will correspond to two different branches coming out from the comparison. On the left-hand side, this represents A is less than B. On the right-hand side, it represents A is greater than B. Then after we have made the first comparison, then it will always make the second comparison of comparing B with C. So we have B and C here. And after that, we will always make a third comparison of comparing A and C. Now we will see the corresponding leaf. Here we have marked A, B, C. So let's see what does it mean. So this leaf corresponds to receiving the result of A is less than B, and then B is less than C, and then A is less than C. So in that case, there is only one possible sorting order of the three items. A must be the smallest, B in the middle, and C must be the largest. So we write A, B, C here. And let's look at this one. Okay, this one says A is greater than B, and then B is smaller than C, and then A is smaller than C. So in that case, after doing some calculation, we will find out that there is only one possible sorting order, BAC, that could correspond to the sequence of results here. And then if you look at this one says A is less than B, and then B is less than C, but A is greater than C, and then we find that it is impossible. So this is a decision tree that corresponds to the previous algorithm. We will see that for all different possible inputs of the sorting order, there will be a corresponding leaf, such that after making a series of comparison, we will reach the corresponding sorting order. Okay, let's see another example. So here, we will find out that the previous method always uses three comparisons, because no matter what happens, we will always compare A and B at the first step, compare B and C at the second step, and compare A and C at the third step. But we may design a cleverer method so that sometimes it just uses two comparisons only. So what we do? So first, at step 1, we will compare A and B and check if A is less than B. In step 2, we will check if B is less than C. But then for the third step, we will compare A and C only if the results of the first two steps are different. So what does that mean? It means that if A is less than B and also B is less than C, then we will not make the third comparison. Or similarly, if A is greater than B and B is greater than C, so if these two are no, okay, then we will also not compare A and C. And in that case, the corresponding decision tree will look like this. And then we will see that for the sorting order A, B, C, it will go through the first comparison, and then the second comparison, and that's it. So sometimes, for some sorting order, we will make three comparisons. And for some sorting order, it will make only two comparisons. Now we will see some common thing or properties of a decision tree. For any comparison sort that works on n distinct items, the first property is that we will see that the decision tree is always a binary tree, because the result of a comparison is always either one smaller than the other or the opposite. So there are always only two possible outcomes of a decision of a comparison. So in that case, the decision tree is always binary. Now the second thing here is the decision tree will have n factorial leaves at least, because it needs to handle all possible order of the input of n items. So here we have 3 items A, B, C. So in that case, we must have one leaf at least, okay, here, one leaf for each possible order. When we have n items in general, there will be n factorial different sorting orders. So in that case, it must have at least n factorial leaves. So here, this decision tree has n factorial leaves, and the earlier one will have more than, okay, so here, because it has some impossible cases, so it will have more than n factorial leaves. So at least n factorial leaves. Now, combining these two facts, we will see that if we consider the node height of the decision tree, it must be at least log of n factorial, because otherwise we cannot have a decision tree of height h can have at most 2 to the power h leaves. So in that case, the height of h must allow us to expand the tree in such a way that the number of leaves could be greater than or equal to n factorial. So it must have at least log of n factorial as its height. Now, the value of log of n factorial, so if we look carefully, what is n factorial? N factorial is n times n minus 1 times n minus 2, and so on and so forth up to 1. So this one can be expressed as log of n plus log of n minus 1 plus log of n minus 2, and so on and so forth. There are n terms all together here, adding up together. But if we check only roughly the first half of them, we will see that the first n over 2 terms each will have values greater than or equal to log of n over 2. So in that case, the sum of these n values will be greater than or equal to the sum of the first n over 2 values. And the sum of the first n over 2 values will be greater than or equal to n over 2 times log of n over 2. So this is of the omega of n log n. So now we know that the height of a decision tree cannot be too small. It is at least n log n. So in that case, for any comparison sorts, the worst case number of comparisons, which means that the number of decisions or the number of comparisons that we need to make on a certain sorting order, it will be equal to the node height of the decision tree. And then in the previous slide, we find that it is at least n log n. So the proof of the main theorem of this lecture completes. Thank you.